In this video, we're going to be looking at kind of a long example of method of joints. And so in this example, we have over 20 members of this truss that we need to determine all of the member forces for, whether they're in tension compression, and if there are any zero force members. So when you're given a really big truss like this, or anytime you're approaching a truss problem, it's easiest to identify zero force members first and then work your way from there, because then you know if you have any members that you really don't need to be solving for. So as we look at this one, we want to identify our zero force members, and again, it's anywhere where a member is intersecting two members that are collinear and no load is applied, no forces on that joint, or anywhere that you have two singular members coming together that are non-collinear and they don't have a load on them. So in this case, if I start from the left, I can already see that member BL is going to be a zero force member because AL and LK are collinear, and then BL is attempting to intersect them, but it's going to take on no load. And if I look at joint B, now that I know BL is a zero force member, I know that BK is a zero force member for the same reason, right? If BL is eliminated, BK is going to be eliminated because now it's the only one bisecting between ABC. And then by that same logic, CK is going to be a zero force member now that BK is gone. If we're looking at joint K, LJK, we're going to have that CK be a zero force member. Now, this doesn't hold true for CJ because there is a load applied at point C. So CJ is going to have some loading on it. So we'll have to move on from that. CJ and DJ are both going to have loads. So if I keep looking down the line, I can see, okay, well, FH bisects IHG, so this will be a zero force member. And then again, by that logic, FI is a zero force member. And I can kind of do this little hopscotch thing now that, again, if FI is a zero force member, then EI has to be a zero force member too, because it's bisecting JIH. And then again, I travel on down the line. EJ is now a zero force member just by deduction, just because all of these ones were zero force members. Again, we already know CJ and DJ are not zero force members. They're going to be bearing some of the load. But out of our 20 some odd members, we've now been able to eliminate 7 of them just by saying, okay, these ones are going to be the zero force members. I don't actually need to take these into account. I can go ahead and say in my final answer, I can either say that these are my zero force members and list them out. Right, so I have BL, BK, CK, EJ, EI, FI, FH. So I could list them out in a little table like this, or as I'm writing each one of my members out, I can say things like, all right, BL equals 0 newtons. You can write them out either way, just as long as they're all accounted for somehow in your final answer, whether they're just in a list like this or you do actually note BL equals 0 newtons. Either way is totally fine. So now that we have that, we didn't necessarily have to do that step first, but it is going to save us some time. Now that we have that, I'm going to go ahead and proceed with my first step in method of joints, which is the free body diagram for the entire truss. And again, when we're doing this free body diagram, I really don't need to care about the inside at all. I didn't need to find these zero force members first. I'm just going to be taking a look at the outside of my truss here. It's kind of a miniature version of it, where I have my reaction support in the y direction at G, a reaction support in the y direction at A, as well as X, since A is a pinned connection while G is a roller connection. And then those external applied loads. So at point D, I have the 400 newtons, and at C, I have the 300 newton applied load. And this would be my full free body diagram for the truss itself, right? We're just really looking at the external portion of the truss. And I'm going to go ahead and apply my equilibrium equations to solve for what these reaction forces are. So typically we want to start with a moment. It's going to get rid of most things. If I take a moment about A, then my only unknown is going to be gy. If I take a moment about A, equilibrium equals 0, then I'm going to have negative 300 Newton force, right, going clockwise, so it's in the opposite direction, negative 300 times 4 meters away, right, this distance here, this 4 meters. Moving to the 400, again, negative, going clockwise, now 6 meters away, plus gy, which is 12 meters, this total distance 12 meters from point A. And it would be pointed up as I've drawn it, so going in the counterclockwise direction. So if I solve this, I get gy equals 300 newtons, and I assume the right direction. It is in the positive y direction, pointing up. So now that I have that, I can pretty easily solve my y equilibrium equation, which would be negative 300 minus 400, since they're both in the negative y direction, plus the 300 from gy, right? This is gy here, plus ay. So again, another pretty simple one to solve. I'm going to get my ay is a positive 400 newtons up. That's two of my reactions. My last reaction is AX, which may have been the easiest one out of all of them because there are no X forces, right? AX equals 0. It's the only one I have drawn on here. There are no X forces, so it is just 0. So easy enough. Now, even though my question didn't ask me to solve for any of these reaction forces, I need them so that I can start solving this by method of joints, right? So that I can pick a joint to start with. In this case, it's going to be either A or G. Pick one of those joints to start with, and then do my equilibrium equations for each joint going down the truss until I solve for every single member. It does take a while, right? Because you're going from joint to joint to joint to joint for these 10 plus members that we have that are not zero force members. So you'll have to repeat the process multiple times for multiple joints. But because we have these reactions, we know we can start at A or G because we'll have some known values with 2 unknowns and our 2 force equations. So I'm going to get rid of all of this. Move these guys out of the way. And I'm just going to make note of my reactions down here. I don't need that free body diagram anymore now that I've solved for all of my reactions. But we had AY was a positive 400 newtons. GY was a positive 300 newtons. So I'll keep that in the corner just for reference for myself. And then start on our method of joints. For me, I usually start to the left and I kind of work my way to the right just because that's how I read things. It's how my brain kind of thinks about these things, but it's totally okay to start at point G if you want to. But I'm going to start for this example at joint A. So at joint A, our process again, draw the free body diagram and solve your equilibrium equations. So at joint A, I have that 400 Newton force acting upward towards the joint, right? Acting upwards. And then I have the force towards AB. That's an A. It's a little sloppy. That's an AB. And then the member force in AL. So two unknowns, two equations. Should be able to solve this with my force equilibrium equations. Right, so sum of forces in the y direction equals 0 is going to be my 400 newtons from AY plus the y component of AB. And you might be a little confused, like, what is the angle of AB? What direction is this going? But we see that we have these 3 meter height on the side, and that every increment here is 2 meters. So in this triangle, what I have is I have 6 meters along the bottom, 3 meters up. So here I have a triangle that is a 1, 2, square root 5 triangle. Now again, you can take the inverse sine and turn this into an angle if you want, but I'm going to leave it as just the ratio. So that I have 400 plus the y component is 1 over square root 5 AB. So even though we weren't given an angle, we can use, by geometry of the truss, we can figure out what the angle slopes of these triangles are. Here I have 1 over square root 5 AB, which means my assumed direction is wrong, right? When I do this math, I get AB is a negative 894 newtons, which means that it is not acting in tension, right? The force is not pointing away from the joint, it's actually pointing towards the joint. So 894 newtons in compression, right? Which is going to affect the way that I solve my x equilibrium equation. Because now when I set up my x equilibrium equation, I want to make sure that this negative 894 is negative, right? Because the actual joint is pointing this way. The actual force on that joint is pointing that way. So negative 894 times the x component, 2 over square root 5, plus AL, giving me the force in member AL of 800 newtons, and it ended up being positive, so this is in tension. So every time you solve one of these joints, it is probably going to give you just these two answers, right? 2 equilibrium equations give you 2 member force answers. But by powers of deduction, we can say, okay, well, I know that I have 0 force members here, right? If I move on to the next joint at B, BL and BK are 0 force members. So therefore, AB and BC have to have the exact same forces going through them, right? To be in equilibrium with each other, since they are the only 2 forces meeting at that point. So by deduction, I don't even have to set up a free body diagram for point B. I can just say, well, BC has to be equal to AB. They have to be exactly the same to be in equilibrium. And I can say the same thing for LK, right? AL and LK have to be the exact same. Right, these 2 meet at this point here, at joint L. Don't need a free body diagram for L. If I did have one at L, it would look like this, right? So it'd be pretty easy to determine, okay, those 2 forces have to be equal. If at L I have my 800 newtons in tension this way, then KL has to be 800 newtons for this to be in equilibrium. Without even setting up my equation, I can just deduce that by looking at it. So KL has to be 800 newtons in tension to be in equilibrium with AL. And then again, by that same thought process, if I bring it on down, again, there's no connections. There's zero force members at K, so it's only KL and KJ that have the forces. So KJ also must be 800 newtons in tension. So just from knowing the zero force members and solving at joint A, I was able to get 5 different members solved of my truss. Now, I can't make the same deductions once I get to JI because I've got, CJ and DJ there. They're contributing forces. They're not going to be exactly equal. As well as the BC and CD because, again, I have the 300 Newton applied load now, as well as members CJ. So I don't need to do them at points B or L or K, but I will need to do them at C or J because now the equations are different, right? It's not exactly all one straight line. So let's go ahead and move on to the next joint. These would be my first 5 answers, and then I would move on to another joint. Again, you could go back and you could do joint G if you wanted to, or you could just keep kind of walking down left to right, picking the joints that make sense to you. You could do C or J, either one, except that if you try to do joint J, you're going to run into a problem of having 3 unknown members. So really your best choices are going to be either do joint C or joint G. I'm going to do C, just because I like working left to right. I'll do my next one. At C, I have that 300 newtons pointing down on it. And then I have my CJ, as well as CD. And then I just found this BC force, right? Which I drew the wrong way. We found it was in compression. Let me draw that correctly. We found it was in compression, so arrow pointing in towards the joint. This is BC, which we found was 894 newtons in compression. So now as I set up my equilibrium equations, they're a little more complicated, right? Almost everybody's going to have a piece of these. So my Fy equilibrium equation is going to be that negative 300 plus 894. Again, it uses that 1 square root 5, same ratio that it had before. 1 over square root of 5 plus CD, which again uses that same 1 over square root 5 since they fall all along that same slope line. But notice that CJ does not. CJ has a different slope here, where this is 2 meters now, and this is 2 meters. So this is actually a 45-degree angle. Right? CJ is down at a 45-degree angle. So CJ is minus in the y direction. Writing down in the y direction, minus CJ sine 45. So I have 2 unknowns in this equation, so I can't solve it outright. I'm going to need to set up my x equilibrium equation, which is going to be my 894, 894 times 2 over square root 5, my x component of the 894, and that's going the positive x direction. I think all of these I have drawn in the positive x direction. So plus the x component of CD, is that, again, 2 over square root 5 ratio, plus the x component of CJ. It's going to be CJ cosine 45. So again, now I have 2 equations, 2 unknowns. I have to solve this as a system of equations. I can't just solve one of them, I have to solve both simultaneously. So if I plug this into a calculator, I solve this, I do the algebra, I'm going to get CD is 671 newtons. That came out negative, so it's in compression. And CJ is 283 newtons, again that came out negative, so it is also in compression. So from joint C, I can't really make any deductions using zero force members. There aren't really any zero force members around C that we haven't already used. So I'm going to continue on to the next joint, which logically feels like joint D. So I'll do another free body diagram, now at D. I've got 7 of my members solved, but I need to get all forces in all members. So at D, my free body diagram, I have that applied 400 Newton force coming from the top. CD, we said was in compression, so it's pointing towards our point at D. 671 newtons. And then I'm going to assume DJ and DE are both in tension before we do the math and figure it out. Again, just my free body diagram, setting up my equilibrium equations. Do my x1 this time first. Sum of forces in the x direction equals 0. Equals the x component of that 671 plus the x component of DE. So again, they have the same slopes, just opposite directions. So my DE is actually pointing in the wrong direction. DE is going to equal 671 newtons in compression. Do my y forces, y force equilibrium here. I'm going to have 1/5 the y component of 671 plus my y component of DE, which remember is now pointing in the opposite direction, so it is a plus. It is, DE is actually pointing up. Plus 1/5 671 for our DE minus 400 minus DJ. So I get DJ equals a positive 200 newtons. And I got a positive answer, so even though that means the DJ is actually pointing down, so it's in tension. And now that I know these, I can walk down my line. If I have DE, I know DE and EF have to be equal because of the zero force members. So EF is going to be the same as DE, 671 newtons in compression. And then again, EF and FG have to be the same because of all of the zero force members there. FG is also 671 in compression. So those are all the deductions I could make about the zero force members there, because then when I get to G, I have that reaction force that I have to account for. So really my last options here are I can do a free body diagram about point J or about point G. And that will be my final members. The only members I'm missing are GH, HI, and IJ, which we can see again, IJ and HI are going to be the same, right, with all the zero force members there. So I'm going to do my final joint. My final joint here, I'm going to pick G. So at G, I have the 300 Newton reaction force from GY. Right, that was from GY. The 671 newtons in compression coming from that FG, and then assuming GH is in tension. There's my free body diagram at G. If I go ahead and do my X component equilibrium equation, right? It's not going to make any sense to do my Y equilibrium equation because I already know everything in the Y directions. So I'm going to have negative GH plus 671 times the X component of that, which is 2 over square root 5. I get GH is 600 newtons, and it came out positive, so it is in tension. And then again, by deduction, I can say, okay, if GH is 600, then HI must also be 600 newtons in tension. And then walking it on down, because of all of those zero force members, IJ also has to be 600 newtons in tension. And those are all of our members now, right? If we walk back and look at every single member, we have identified our zero force members and then solved for everything that was bearing a load, right? So that's an example of how we would do method of joints. Again, just setting up, identifying your zero force members, setting up your initial truss free body diagram to solve for reaction forces, and then going down joint by joint to solve for every member using the equilibrium equation. In the next video, we're going to talk about another method of how you can solve these trusses called method of sections. So we have two main methods to solve these, method of joints and method of sections. Both are totally acceptable. They're just going to be different ways to work out the same problem.